Hey folks, how's it going? This is Mr. Murray coming to you with a video on exponential equations. So in this video, I'm going to talk to you about how to solve equations, how to find the value of x when x is in an exponent. Now, I want to start off by saying that this is going to be a very basic intro to these types of equations. It's going to involve um, only a very straightforward approach. And I'm going to tell you that in many cases, you are not going to be able to find an exact answer to these problems. And unfortunately, until we learn the strategy of logarithms, it's going to be pretty challenging to solve some of the problems. So right now, at least for the time being, I'm going to solve you problems where we're going to be able to use this really straightforward rule to find the value of x, and kind of any other scenario, I would say probably give me an estimate. All right, so the point of this video is kind of just to introduce you to this, to break down the important ideas, and then to kind of provide opportunities for me, you, and us to practice with them. Okay, so an exponential equation. What is an exponential equation? Well, as its name suggests, an exponential equation is any equation that involves one or more exponential expressions. And an exponential expression is one of these things that are, for example, 2 to the power of x. It's called an exponential expression because alone it is just simply like a statement. 2 to the power of x, right? It's not a complete sentence. Whereas 2 to the power of x equals 8 would be a complete sentence, okay? So 2 to the power of x is an expression, and the role that x plays in this expression is it is in the exponent. So I call it an exponential expression. Now, if 2 to the x equals 8, a challenge we could try to determine would be, well, what x makes this true? Now, if we look on the graph here, we can see that this is a graph of 2 to the x. It appears that 2 to the third is equal to 8. So in other words, 2 to the x is the same thing as 2 cubed. So you can think about, if this is true, what x would need to be. Over here, we see a similar thing, right? 1/2 to the power of x equals a half cubed. And we'll have to think about, do the same kind of ideas that work with exponential equations when we're working with kind of integers or whole numbers apply when we're working with rationals or kind of like fractions, right? So it's all kinds of things we have to think about. All right. So the basic idea that allows us to solve exponential equations is called the one-to-one property. So the one-to-one property says that two exponential expressions with the same base will have equal exponents if and only if those expressions are equal to one another. Okay? So to break that down, what that means is if you have two expressions that are equal to one another and their bases are the same, then their exponents are also the same. And also, if you know that two numbers are equal to each other, then if you make them exponents of the same base, then these expressions will be equal to each other. So for example, right, we know that let's let x equal 4 and y equal 4, right? X and y are equal. So 5 to the power of 4, is it true that 5 to the power of 4 equals 5 to the power of 4? Yeah, of course, right? These things are clearly equal to each other. 625, 625. Okay, that's an example there. So this is what we call the one-to-one property. And it comes from, if you believe it or not, the nature of this graph. So this year we learned about what's called a vertical line test. And I drew a horizontal line, but maybe I'll start with a vertical line. The vertical line test says that if I can run this vertical line across the function, as you see here, and it only touches the graph in one place each time, this vertical line, then the graph is a function. So that shows that these two graphs are functions. But one thing we're going to talk about next year is that there's also a test called the horizontal line test. And if a function's graph passes the horizontal line test, see, I'm going to make that mistake a bunch. So if a function's graph passes this horizontal line test, then it means the function is 1-to-1, which means that every output only belongs to one input. In other words, no outputs ever get repeated, right? Like with a parabola, how you know there's a bunch of outputs that are the same except for the vertex. Here you can see that all of the outputs are different. So that means that if two expressions are equal to each other and they came from the same graph, the graph of 2 to the x, the graph of 2 to the x, and the outputs are equal, then you know for a fact that the inputs must also be equal. Here's where it's not true. Let's say we had x squared. Okay? This is not 1-to-1 because -2, f of -2 is equal to the same as f of +2, right? They're equal to 4. So if I said that I don't know, if I said that x squared was equal to 4, right, as we saw from the last unit, you can't tell me for sure what x is equal to. Yeah, it could be 2, but it also could be -2. In this situation where I tell you 2 to the x is equal to 2 to the 3, no, x can only be equal to 3. And that comes from this idea of being 1-to-1. All right, and this is and that's where this 1-to-1 property also gets its name. Okay, so a thing to remember is assume that a cannot be equal to 0. That would be a very boring flat line. But mathematicians like to state those important, sometimes overlooked or taken for granted facts. Here's another example. So if 2 to the x plus 3 equals 8, well, since 8 is equal to 2 to the 2 cubes, then 2 to the x plus 3 is the same as 2 cubes. And because of the 1-to-1 property, we know that because these outputs are the same, right? If you think about the graph of 2 to the x, then the inputs, x plus 3 and 3, must also be equal, right? And so that means x is 0. So this is the underlying idea behind how we are going to go about solving these problems. So this is getting at the wonderful overlaps that we see in math, right? So when we are talking about solving absolute value equations way back, probably November and or December, right? I said we talked about bars alone. So I said in bars alone, right, the goal is you have to get the bars alone. Sometimes the bars are by themselves, such as in the absolute value of x plus 2 is equal to 6. Sometimes they weren't. And so when they weren't, right, you'd have to divide by -2, and you get x plus 3 equals -5. And at that point, you'd say no solution because you can't have a negative absolute value. So basically, right, that's the idea. Either the bars were alone or we got them alone. When we started to solve by taking the perfect squares, or rather by taking square roots, I guess I should say, whenever we had a perfect square, the goal was to get it alone. So sometimes in the case of x squared equals 16, it was already alone and we could just square root both sides. In the case of this stuff, first we might have to, subtract 5. Then we'd have to divide by 2. And then we'd kind of go from there. Okay, so we had to get the squares alone, and then once the squares are alone, we could take the square root and go from there. Now we're in what I call bases alone. So essentially, we need to make sure that whatever that base is that has the exponent in it, we have to get that alone. We have to try to get the other side. We have to turn it into an equivalent expression with the same base, and then use the 1-to-1 property to eliminate the bases and bring the exponents down. So for example, because 2 to the x plus 2 is equal to 2 to the 4, because those bases are the same and they're equal to each other, x plus 2 has to be equal to 4. okay, because of the one-to-one property. All right, folks, so let's jump into some problems for me to do, and hopefully this will give you a sense of where the problem-solving strategies that I've discussed are kind of going to come in here. So remember, the idea is first, whatever has the exponent on it with the x, we get that alone. Then we're going to rewrite the other side, whatever's left, in terms of the base, so we can have the bases the same. Then we're going to take the exponents and we're going to make them equal using the one-to-one property, and then we're going to solve for x. So here, for example, my base is already alone. It's 2 to the x plus 2, right? This is my base. It's alone. So now I'm going to look at 16, and I'm going to ask myself, well, can I write that as 2 to the power of some number? And the answer is yes. It's 2 to the power of 4, because 2 times 2 times 2 times 2 is equal to 16. So 2 to the x plus 2, instead of writing 16, we're going to write an equivalent expression. But now, because both bases are 2, and these things are equal to each other, the exponents must also be equal because of the one-to-one property. And then solving for x, we have x is equal to 2. Please just remember, if you are asked to solve an equation, I'm asking you for any variables that you're being given, what are the values of those variables that are going to make the equation true. In this case, you're only going to be working with one letter, but we've seen systems of equations and such where 2 letters could be a possibility. Let's look at the next one. In this case, the bars are also, silly me, the bases are alone, right? 4, the base is alone, there's nothing in front of it, there's nothing off to the side. So I'm going to go ahead and I'm going to try to write 64 as a power of 4. So I know that 64 is equal to 4 to the power of 3, because 4 times 4 is 16, and 4 times 16 is 64. So 4 to the 2x plus 3 is equal to 4 cubed. So by the one-to-one property, because these exponential expressions are equal and the bases are the same, the exponents must be equal. So 2x plus 3 equals 3. So 2x equals 0. So x is equal to 0. Okay, so please make sure you understood what I did in this little segment here with how I started to solve these. If you have any questions, please make note of them and or maybe go back and review this part. And then when you're ready, I'm going to go ahead and move on to some more problems. Alright, I'm going to turn up the heat a little bit, and in these problems you're going to notice that the bases are not alone by default. So here, notice I've got a 2 in front of the base I want to make go away. So I'm going to divide by 2, because dividing by 2 cancels out this 2. And now over here, notice how I get, conveniently, 49. So the base is alone, 7, the number with the x and the exponent, right? That base is alone. So now what I'm ready to do is I'm ready to see if I can write what's left on the right as a power of 7. You're only going to be doing this analysis once the base is alone. So 49 is 7 to the power of 2. Now, because these expressions are equal and the bases are the same, because of the one-to-one property, the exponents also must be equal. That is to say, x minus 5 must be 2, and 7 is the number which, when you subtract 5, gives you 2, and you can see it by adding 5, and so therefore 7 is the answer. Here we got to do a couple things. So remember, we're going to first start by subtracting. Imagine that. So if you're having problems visualizing this, imagine this was a y. Imagine I wanted you to solve 2y plus 15 is 177. How would you solve that? First, you would subtract 15. then you would divide by 2. So it's the same exact idea, right? First you subtract 15. And you get 2 times something equals 162. And then you divide by 2, and you're back to that thing being equal to 81. And then when you think about it, you realize that thing that you kind of wanted to pretend wasn't there was just 3 to the x plus 10. And there you are. Now the base is alone. So I've got bases alone. And if you don't want to use that strategy, that's okay. That's just a little visualization and just a kind of little like substitution technique to show you that it's really not that bad. It's just like getting any variable alone, getting the base alone, right? Just like getting the bars alone, just like getting the square alone, right? There's so much really nice overlap there. So 81 is 3 times 3 times 3 times 3, right? So you can see again, I made the bases equal. So since the bases are equal, the expressions are equal, the exponents are equal. So x plus 10 is 4. So x therefore is equal to -6. Okay, so this is just a little bit more difficult examples, but the major difference here is that we're just taking it one little step further by, instead of starting with the base already alone, maybe taking 1 or 2 steps to get the base alone before solving for x and using the one-to-one property. All right. Now for some ones with we do's. Now in the we do problems, what I'm going to do here is I'm going to kind of see if you guys can help me out with the fundamentals, but you can notice the difference here, hopefully, and that's that we are working with fractions. But the good news is fractions are our friends, and it's going to work exactly the same way. So here, what would be my first step? I would start by trying to make what? Get the base alone. So is the base alone for the first one? Yes, there's no number in front. The base is alone. Now what I need to do is I need to turn 4 over 25 into a power of what over what? Into a power of 2 over 5. Because the one-to-one rule is not going to work unless the base here on the left is equal to the base on the right. Okay, so folks, here's going to be my little secret here. Just remember, whenever you're working with a fraction, a over b to the power of c, remember that essentially you're just distributing the exponent to the top and to the bottom. So essentially, if I can figure out what is going to make the 2 equal to 4, or whatever will make whatever power I need to make the smaller number to work with the smaller number, then I'm most likely going to have the same thing work out with the bigger number. So for example, I just look to the 4 and I say, okay, well, this needs to be 2, so I get 2 squared equals 4. And then I notice, oh look, 5 squared is also 25, so everything works out. So 2/5 to the x plus 2 equals 2/5 squared. And so x plus 2 has got to be equal to 2. And so x is equal to 0. All right, next one. So here I have to start by doing what? Getting the bases alone. Okay, is the base alone? It is not. We need to divide by what? By 5. Okay. So here I get 1/4 to the 2x is 64. But how am I going to get this as a power of a quarter, right? Because now the bases are alone. Just remember, what's the trick to getting that 1/4 to turn into a whole number? It's to make the power negative. Because remember, 1/4 to the power of negative x, or I don't know, 1/4 to the power of -1 is equal to 4 over 1 to the power of positive 1, which equals 4 over 1, right? So now I got to think about, okay, well, 1 over 4 to the power of negative 2 equals, remember you flip it, and then you make the exponent positive. So it's 4 squared, which is 16. 1 quarter to the negative 3 equals 4 over 1. Remember, flip it, make the power positive, and 4 cubed is 64. So 1/4 to the 2x equals 1/4 to the negative 3. Remember, the negative gives it the flip, the 3 gives you the 64. So 2x equals negative 3, meaning x is negative 1.5. Okay, so please make sure you understood what we did in these we do activities, because at this point I am getting ready to turn it over to you. All right, folks, so now we're on to some problems for you to do. So what I have here is 4 equations, exponential equations, all right? And you can see here that they are getting increasingly difficult as we go from top to bottom. But our goal here is just to simply apply the rules of exponential equations that we've seen before, right? Our idea of the one-to-one property, right? Some of the things we may have recapped about how exponents work with fractions. If you need to go and review anything, I'd recommend you do that before we do this activity. And that includes if you need to skip around using the timestamps in the description below. So when you're ready, please go ahead, pause the video, find all values of x for each of these 4 equations. There should be 1 per equation. Then when you're ready, unpause, and you can see what I got. All right, so here we go. So in the first, or each one, right, we got to ask, is the base alone? All right, in the first one we know, no, it's not. We got to start by dividing by 2. So 3 to the x is equal to 9. Okay, now the base is alone, so we're going to rewrite 9 as a power of 3. So we know that 9 is equal to 3 times 3, so it's 3 squared. So that means for this to be true, we need x is equal to 2. Okay, next one, we need to again start by getting the base alone, and in this case it is not. So I have 4 to the 3x minus 15 equals 256. 256 is 4 to the 4. You could play around with powers of 4 and kind of figure that out. Or to kind of, right, guess and check. So 3x minus 15 is equal to 4. So 3x equals 19. So x is equal to 19 thirds. Now what you really want to be doing is you do really want to be checking your work. So kind of so that I'm practicing what I'm preaching. 2, all right, let's say I plug in 2. So if I do 2, this is 2. 3 squared is 9. 2 times 9 is 18. If I plug in 19 thirds, well, when I do the 3 times the 19 thirds, the 3's are going to cancel. Then what I'm going to do is it's going to be 19 minus 15, that's 4. So it's going to be 4 to the 4, which is 256, times negative 2 is negative 512 rather, so that checks out. All right. This next one, we need to combine what we know about fractions. And that's that we need to think about our numerator and denominator. Now, in this case, right, we already know the exponents alone, right, the base alone. So I need to think about, this is going to be 3/15 to the power of something. And to figure that out, I'm going to start by looking up, and I know some of you might say 3/15, Mr. Murray, that's the same thing as 1/5. Can't I just simplify it? And most likely the answer would be yes. And if you could probably simplify the one on the right-hand side too. But for all intents and purposes, let's think about how we would make 3, what exponent would make it equal to 27, and that would be 3, because 3 times 3 times 3 is 27. And so chances are, and this is actually true, that the bottom number to the power of 3 also equals that denominator. Okay, so that's, it might seem difficult, but you just stick to just trying it out with the smallest numbers, because the idea is 3/15 cubed is 3 cubed over 15 cubed. So you solve for 1, and then it most likely 99.99% of the time will work out for the other. So 3/15 to the x minus 2 is equal to 3/15 squared. So x minus 2 is equal to 3, rather 3/15 cubed. So x minus 2 is equal to 3. So x is equal to 5. If we check the work, 5 minus 2 is 3. And evaluating, 3 cubed is 27, and 15 cubed would get us 3375. On to the last one. Here the major difference is you need to start by multiplying first. So multiplying by 3 cancels that. Multiplying by 3 here gives you 2/9 to the 0.5x equals 729 over 8. Because 243 cubed is 243 times 3 is 729. Now here we can be like, all right, well look, 2 cubed is 8. You might know that 9, well 729, that looks like it's going to be something with a 9 in it. Now, let's see what I get. So I plug in my calculator and I find that 9 cubed is equal to 729. So 9 cubed is the top, 2 cubed is the bottom. So here's what I do. I take the 2/9 and I make it negative. So the 9 comes up and the 2 goes down. And then I do my 3, because this is equal to 9/2 to the positive 3. And then we see that the 9 to the 9 to the positive 3 is 729, and 2 to the positive 3 is 8. So we'll link this together and we'll get 2/9 to the 0.5x is equal to 2/9 to the negative 3. So 0.5x equals negative 3. So x equals negative 6. Yay! And let's check that out. I plug it in. Negative 6 times 0.5 is negative 3. 9/2, or 2/9 to the negative 3 is 9/2 to the positive 3, which is 729/8. 729/8 to the 1/3 will give me 243/8. Okay, so that's the idea. Step 1. All right, so let's recap this idea. Step 1, bases alone. Use your basic arithmetic and algebra skills to pretend like the base with the x on it, the exponent with that x in it, it's a variable, get it alone. Step 2, apply the one-to-one property to rewrite the left-hand side and the right-hand side, okay, so that they're equal and they're exponential expressions that have the same base. For example, 2 to the x plus 3 and taking the 8 and making it equal to 2/3. So that 2 to the x plus 3 is equivalent to 2/3, meaning that I can then use the one-to-one property to bring down the x plus 3 and the 3 and only work with solving those exponents, because we know that if two exponential expressions are equal and their bases are the same, then because these are what we call one-to-one functions, their exponent values must also be the same. So hopefully you're able to find this video helpful. Please make sure you take a look at the activities that I planned out for today to help you get some practice with this. It is something we'll be talking about most likely in our hangout, but we are going to be wrapping up this unit. So it's important that if you have any lingering questions, at least in 2019, 2020, we're wrapping up. And so if that continues to be the case and you have questions, please feel free to reach out to me at any time and to attend office hours and any hangouts. All right, but best of luck. Don't forget to love math, and remember, you can do it. Until next time, have a wonderful